Hello, CDCon community, and welcome to the session on adoption of DevSecOps practices in regulated industries. I'm Gurpreet Sachdeva, and I'm a cloud and DevSecOps architect in Capgemini, India. I'm a co-founder of Delhi NCR Java user group and regularly blog on Java and DevOps related topics. I've written a book on ELK stack and also launched a video course on DevSecOps. You can find me on Twitter and LinkedIn. These are my coordinates. In this session today, I want to talk about how DevSecOps practices can be used to make software reliably and comply with standards in regulated industries like aerospace and defense. There is a growing usage of software in different industries, and regulated industries face unique challenges in adoption of DevSecOps and Agile practices. While DevSecOps emerged from internet and software companies, the same principles can be used in other industries as well to increase throughput, reduce cycle time, and perform continuous security verification. The DevOps movement had its origins in the seminal talk given by John Alspaugh and Paul Hammond of Flickr at the O'Reilly Velocity 2009 conference. They described how they can perform 10 deployments per day, and this approach became popular as DevOps. The born in the web companies like Amazon, Facebook, Google, Netflix, and many others laid the foundations of DevOps movement and popularized these practices. Adoption of DevOps practices leads to tremendous benefits in terms of throughput and system stability. The Accelerate State of DevOps report points out adoption of DevOps practices transforms normal teams into elite teams. These elite teams have significantly better deployments, lead time, incident recovery time, and lower change failure rate as compared to low-performing teams. We have seen that from military drones to MRI scanners, energy control systems, fighter jets, and modern cars, we find significant amount of software being used these days. Modern cars have become like a computer on wheels. For a comparison, fighter jets in World War II did not have any software, whereas modern fighter jets have 8 million lines of code. It becomes pertinent that the regulated industries start imbibing the best practices and strategies of a software company to make successful products. The apparent contradictions between certain aspects of Agile Manifesto and SDLC practices of regulatory industries have delayed the adoption of Agile. The Agile Manifesto gives importance to individuals and interactions over processes, but regulated industries have to follow controlled processes in order to make safe software, which is compliant to different standards. Another gem from the Agile Manifesto is working software over comprehensive documentation. In case of regulated and critical software, sufficient documentation is required to demonstrate that all adequate steps have been followed to make a safe software which is compliant to different standards. The Agile Manifesto also advocates responding to change over following a plan. Regulated software is developed with detailed plans and proper risk identification and mitigation strategies in place. As you can see, there are apparent contradictions between the philosophy of Agile Manifesto and the way regulated software is typically built. This has led to delay in adoption of Agile and DevOps practices in regulated industries. There are some unique challenges which we see when we want to adopt DevSecOps practices in regulated industries. First and foremost, regulated industries like aerospace, automotive, and life sciences, etc., must comply with various safety standards like DO-178C, ED-12B, MISRA, ISO 26262, etc. Any compromise in safety standards can lead to drastic consequences. Boeing's reliance on software without adequate safety provisions led to 2 major air crashes. These are very unfortunate incidents. Apparently, the MCAS relied on recently developed software, and in a rush to release it, safety compliances were not stringently done. As companies connect enormous numbers of devices and use cloud platforms, cybersecurity becomes increasingly important. Since we use a lot of third-party and open source software, we must ensure that they are not vulnerable. In case of regulated industries, we also have to comply with security standards like DO326A, ED202A, etc. Traditionally, we have seen that security tests were conducted towards the end of release cycle after all implementation and testing cycles get completed. There are some InfoSec champions who audit the release for security vulnerabilities and publish a whole lot of violations. Often fixing these vulnerabilities can lead to design changes also. Many times this leads to delay in release cycle. But with the increased adoption of Agile practices, the release cycle has shrunk to sprint boundaries of 2 or 3 weeks. So performing security checks after every few months increases the risk of attackers exploiting weaknesses in the production. Security verification is required to be done continuously in the DevOps pipeline. Hence the need for DevSecOps with continuous security verification done throughout the CI/CD pipeline. Regulated software also has to comply with various standards for safety, security, and development practices. For example, the aerospace industry has to comply with DO 178B and C safety standards, NIST SP 800-171 for security, and JSF and MISRA for coding. Similarly, automotive industry has to comply with ISO 26262 safety standards, MISRA, and CERT for security, and AutoSOR for coding. And you can see there are similar standards to be followed in other industries as well. When we start using Agile and DevSecOps practices, we have to make sure that eventually software is compliant with all of these standards. The same model of aircrafts, cars, or medical devices need to be supported for many years. And this leads to huge legacy, code base, and complex branching model. Lack of visibility of actual production environment leads to development environment being inconsistent with runtime environment. It is challenging to compensate for CPU or memory constraints and provide production-like test environments reliably. We have seen that software complexity is exponentially increasing, while development productivity is stagnating. As per a McKinsey report, it is expected by 2030, while the software complexity in automotive sector will increase to 5 times, the software development productivity will increase only to 2 times. Model-based software engineering in V-cycle is a traditional way of development in many industries like aerospace and automotive. It is an extension of waterfall process, with the difference being that the process steps are bent upwards after the coding phase to form the V shape. The process starts with creation of an executable specification linked to original requirements. In system design stage, engineers analyze and interpret the business requirements. Next, the architecture is designed by identifying different components and relationship amongst them. After component design, engineers implement the missing pieces on the top of the auto-generated code. Various simulations like requirement in loop, model in loop, and software in loop are used to verify the specification across different stages. Validation is done through different testing phases like unit, integration, system acceptance, and test for safety and security certifications. Although V model provides two-way traceability between the design and the requirements, it is inflexible for shorter time to market and dynamic schedule. It works well for smaller projects, but for bigger projects, there is an increased risk of defects not being found early enough. The long development cycles and low volume of test automation make the process less flexible to change. So what we need is, we need to transform to a more agile workflow. Adoption of agile planning and development process is the first step in the road to DevSecOps adoption. You can try to do DevOps with waterfall or recycle also, but you will never get the full benefits. We need a transformation from V model to W model, something like a hybrid, between recycle and agile workflow. You may shift to newer tools like Jira or continue using traditional tools like Doors for agile requirements, backlog management, record user stories and requirements corresponding to all non-functional requirements like safety and security. Instead of having longer iterations of V model, plan for shorter iterations to build software incrementally with all development and verification activities completed in a sprint. The initial sprints shall focus on requirement modeling and system design modeling, which can be defined later based on feedback. In each sprint, build a particular component or feature with all activities like component design, implementation, and unit and integration testing. Complete the system testing, acceptance testing, and certification compliance in the final sprints. The same model of aircrafts, cars, or medical devices need to be supported for many years, and this leads to huge legacy code base and complex branching models. Legacy version control systems are still being used. Like there are many systems I've seen in my experience, they're still using ClearCase in automotive and aerospace industry. But as we all know, these version control systems, these legacy version control systems are not natively suitable for CI/CD pipeline and have limited integrations with modern third-party tools. So the need of the hour is to migrate to a modern version control systems like Git or maybe Bitbucket, which integrate much better with the CI/CD pipeline and modern plugins. Auto-generated code shall be compiled, and the binaries can be stored in a repository like Artifactory. This is done to make sure that we don't need to compile the auto-generated code every now and then. The next thing is that we need to optimize the branching strategy to ensure that feature or release branches are more frequently merged back into the master branch. Well, ideally, we would probably like to have one single branch, but it's too much of a thing to ask for when teams have already been working on ClearCase and very, very complex branching models to go straight away into a single branch model. So what I would suggest is go for a hybrid approach, go for an intermittent approach. Maybe we can use something like a Git flow branching model, which may not be the best in the agile world, but still it's an in-between path. So as we know, there's a central master branch and a parallel develop branch that represent latest changes, and nightly, weekly gates run on this branch. After stabilization, changes in develop branch are merged in release branch and tagged with the release number. The develop branch is forked to form release branch, and after release testing, merged back into develop and master branch. With this strategy, we see less conflict in master branch, and develop branch is always in a ready state. At the heart of any successful DevSecOps environment is a continuous delivery pipeline, which can be effective only when testing across different stages is completely automated. Static code analysis reveals potential vulnerabilities such as null pointer problems, buffer overflows, memory leaks, division by zero, etc. It can be automatically triggered from the CI orchestrator like Jenkins. You can set threshold levels for the number and severity of warnings, and the pipeline can be halted if this threshold is reached. Compliance with different standards like MISRA and DO178C can be verified as part of the static analysis. Since we are increasingly using third-party and open source software composition analysis is essential to create a package bill of materials. You can see vulnerable packages and the associated warnings by looking at your BOM. Unit tests can be triggered as soon as any new source code changes are committed. The aim should be to get 100% code coverage by using stubs or mocks to remove hardware dependency. You can correlate test cases with code coverage report to assess the completeness of testing. Functional testing verifies the integration of different units of a module. Test plans can be auto-generated from the system model. Virtual prototypes and simulations like software in loop and hardware in loop can be used to verify all the flows. Folding security in the DevOps ethos of incrementally improving software in smaller and faster builds helps in fixing flaws earlier in the development process. So use the secure by design principles and leverage techniques like threat modeling and data flow diagrams to uncover external risks and identify potential vulnerabilities. Threat modeling documents the key assets and purposely exposes risk to those assets in a thorough and disciplined manner. Select tools which can be integrated with your IDE and help in complying with different coding conventions prescribed by industry forums like OWASP, CWE, CERT, and MISRA. Software composition analysis can be used to enforce the organization's open source software policy and create a list of third-party software being used. Configure your IDE with appropriate static analysis tools, which can run during compilation, so you will come to know of potential vulnerabilities and error-prone code. Vulnerability testing can be done during integration testing phase to find out potential vulnerabilities and estimate the magnitude of risk. In penetration testing, perform full risk assessment by simulating attacks to identify exploitable weaknesses as well as strengths. Follow the fail fast principle, and whenever at any stage security vulnerabilities are found, stop the pipeline, fix the issues, and then move ahead. When we are working specifically with aerospace software, we have to comply with DO 178C safety standards. And one of the very fundamental requirements is to have a bi-directional requirement traceability across all phases if you want to comply with the DO 178C standards. So bi-directional requirement traceability ensures coverage of requirements in design and code, and similarly, there is coverage of design and code in the requirements. While traditionally it is being done manually in Excel sheets or with tools like DOORS, but we want that in a DevSecOps environment, the whole requirement traceability process should be automated. All stakeholders can view and collaborate on all changes across the software development lifecycle. Requirements are maintained in Agile backlog as user stories and tasks, while creating system design and component design link to object models, data models, sequence diagrams to user stories and requirements. Automatic code generators give the ability to trace back directly to the individual parts of the design model from which the code was generated. Source code and unit test code can contain user story ID and reference to design model. Automated scripts can link user story to code change on code commit. Test automation tools can be integrated with a common tool, test asset management tool or repository where all test scenarios, test scripts, and associated results can be stored and traceability established back to code, requirements, and defects. After deploying to production, in case of a defect or incident, map the defect ID to the requirements. The generated documentation should contain reference to requirements and design sections. While developing embedded software, various different simulations like software in loop and hardware in loop can be leveraged. Software in loop simulation represents the integration of compiled production source code into a mathematical model simulation to provide virtual simulation environment for the development and testing of detailed control strategies. Software in loop makes it possible to test software prior to the initialization of the hardware prototyping phase, significantly accelerating the development cycle. It enables the earliest detection of system-level defects or bugs, significantly reducing the cost of later stage troubleshooting when the number and complexity of component interactions is greater. Hardware in loop simulation is a type of real-time simulation to test physical system design. Real-time computer-based models used as virtual representation of physical systems, real-time capable model of the control and the plant. For example, As you can see in this slide, you can see there's a flight simulator which is there, we are trying to do a hardware in loop simulation by using a flight simulators. The benefits which we can get from hardware in loop simulation are less expensive for design changes, as hardware in loop simulation can be performed earlier than validation in the workflow in order to identify and redesign for problems relatively early in the project. Less expensive to schedule hardware in loop simulation and more practical than validation because you can set it up to run on its own. It provides a form of rapid prototyping in which we start with a virtual prototype and move in stages towards a real prototype system involving hardware and software for final design. These primary simulation techniques can be used in conjunction with CI/CD pipeline for automated testing throughout different phases. Just like manufacturing processes contain policies for ensuring end products exhibit strong quality characteristics, similarly, embedded software should be developed in accordance with policies that clearly state quality goals, and compliance with goals should be automatically ensured. A central CI/CD pipeline enables software deployment along with continuous security verification. Sprint planning can be done after backlog creation and prioritization. You can continue with traditional tools like DOORS or start using more popular ones like Jira. For team collaboration, you can use tools like Slack. Requirement modeling should be followed with design modeling and software architecture. You can continue to use tools like SysML or Rhapsody, or go for an Eclipse-based plugin like A4E. Design your models to be executable so that you can run simulations to test your design against requirements before actually building your system or even a prototype. Use policies to define system and component architectures. Now, documentation is another aspect which is very important for safety compliances like DO-178C. But rather than creating big upfront documentation, generate incremental documentation every sprint in CI/CD pipeline. Inputs can be requirement model, system model, component design model, test plans, and source code. Documentation directly generated from source code keeps the documentation consistent with the source code. Additional documentations can be manually created. As part of software design, also consider security aspects and use techniques like threat modeling and data flow diagrams. Source code can be auto-generated from design model or self-written using various kinds of tools like Adacore, MATLAB, Simulink, etc. These are all traditional tools which people have been using in regulated industries from a long time back. Unit testing should be completely automated. During implementation, perform static analysis and source code composition. There are a lot of tools from which you can choose from. The generated binaries should be versioned, tagged, and stored in a repository like JFrog or Artifactory. Deploy the binaries on integration environment leveraging simulations like software in loop, hardware in loop, and even digital twins for that matter. Perform automated functional testing using simulations. Thereafter, perform vulnerability testing to find the potentially weaker areas of system. After this, deploy the binaries or staging environment and leverage hardware prototypes and digital twins. System testing should verify end-to-end scenario, and in the end of cycle, compliance checks can be performed. Automated penetration tests should be performed to break into weak areas of system. There are many tools like Metasploit, MISRA, Burpsuit, W3AF, etc., from which you can choose from. Unlike a SaaS environment, the software cannot be automatically deployed on the production environment, which can be an actual aircraft or an automobile in this case. So this step would be manual, and the end-to-end test cases can be run to verify everything is working fine. DevSecOps not only implies shift left of testing, but also shift right of feedback. After performing different types of testing, any defects, suggestions, or enhancements should be recorded in a tool like Jira. By performing different activities, In an automated CI/CD pipeline, you not only get fully shippable and secure software, but also associated documentation and requirement traceability. So, in summary, by following DevSecOps practices, we do see tremendous benefits in terms of throughput, stability, and security verification. The regulated industries like aerospace and automotive and life sciences can leverage the DevSecOps practices just like the web companies. There are unique challenges in terms of standard compliance, security, and legacy development practices. However, a hybrid model can be used with gradual adoption. This will ensure security and safety compliances are also automated in the CI/CD pipeline. The regulated industries can also get the similar benefits as web companies. I hope you found this talk valuable and you can use some of this insight to use DevSecOps and Agile practices in the regulated software, in the operating software. Now I'll be happy to answer if there are any questions. You may put your questions in the chat window. Thank you. So while we are waiting for questions in the chat window, there are certain key things that generally people ask me whenever I discuss this topic with them, like adoption of DevSecOps practices for regulated industries. First and foremost, people have a concern that, hey, you know what, DevOps is something which people associate typically with a SaaS software model, but can it be used for software which you're running on, let's say, an aircraft or an automotive? So hell yes, we can do that. Obviously, we'll not be able to do an automated test on an aircraft, but certainly we can have simulators, virtual prototypes, we can have digital twins, which can really help us in doing a continuous delivery as such. It may not be a continuous deployment, but we can do quite a lot of automation, end-to-end testing, security verification, and compliance verification in a pipeline. So we do have a question. So the question is that what does imply the manual process of releasing production, which is a plane or car? Yeah, this is what I was trying to say just now, that obviously this is not like, let's say, a cloud environment or a SaaS environment where from, let's say, staging or QA, you can directly deploy your software in the production environment, right? It's not like Amazon.com where you have production tenant and you can deploy directly over there. Here we're talking about an actual aircraft, for example. You would not be able to do that automatically. You'll have to run the embedded software in some kind of a chip and then deploy that, put that on the aircraft. And that is why that last step is manual, which cannot be automated. That's the point here. And while we are waiting for some more questions, another aspect which comes into mind, which people generally ask, is that when we talk about aircraft, etc., and automotive for that matter, the safety is of a paramount concern. And there, of course, as I mentioned in the talk also, that there are different standards, for example, DO-178C to follow when you want to make safe software. The way we have been doing this, the way industry has been doing that has been, really manual. People have been doing code reviews, walkthroughs, and then auditors come and then do a safety analysis and they go through the code pieces. But as I said earlier, if we use policies to define our architecture, our design, and then throughout the SDLC, throughout the Agile DevOps process, the pipeline, we take certain measures, we can do most of the things in an automated manner. For example, you can have your documentation, which is a key part of safety worthiness, that can be generated automatically as part of, let's say, comments in a code, as part of your incident repository. There are tools available which can pull those comments and generate documentation for you. There would be some extra steps required after that, which can be done later, but much most of the part can be done through this. Then bi-directional requirement traceability is another thing which can be done automatically as part of the pipeline by tracing it through your code, design, requirements, etc. So all in all, the concepts of CI/CD can be used to make safer software for regulated industries. With that, I think we're running out of time. I'd like to thank everybody again for attending this session, and hopefully you will get some insight out of it. Thank you so much.